Hello guys, welcome back to Maths on African Motives, still on our engineering science info. This is we are still on our kinematics, that is working with the resultant velocity, that is the resultant velocity or the resulting velocity. And we are going to work this part with the use of the components, all right? I'm going to explain the idea of the components. I think as I was been explaining previously, we've been working with the different methods there, the application of the cosine rule and so forth, whereby you have to use the equivalent triangles that you can have. But in this case, what is it that you can have if we are dealing with components? All right. Resulting velocity is different from the one that we talked about previously. Remember, with a relative velocity. And I explained differently what to do or on the calculations of the relative velocity. Okay, those are two different things. So let me just have something of this nature there. We had a condition whereby under the relative velocity, let me just have this before so that we do not have a confusion. We were saying that if we are given two velocities, we've got the velocity of A and the velocity of B being taken from our compass in this case, right? We do not know according to the information that you're given, but let us assume something of this nature, all right? Whereby maybe this is our A and this is our B. I say that it is the question that matters after you have indicated whatever that you've indicated there. It is the question that matters to say, how are you asked the question? You're asked to find the relative velocity of A with respect to B. If it is with respect to B, I said what you're going to do is to affect the B. You stop B, turn it around, all right? So meaning to say this B that we see here, we are going to turn it around. So it will be that way. So instead, we are going to have now this side. Our B that was on this side is now taken to the other side. So this one, it's no longer applicable, this one that we have here. It's no longer applicable. We are now working with this B. That is the idea of the relative velocity. With respect, the one that is with respect to this one is the one that you change. You stop it, you change the direction, then you add the given what? Velocities. I talked about that, how you're going to take depending with the angles that you're given, the angle here, and also the angle that is taken up to this point, or you can even use this angle as long you understand how to use your velocities in addition. But if you take all your angles, like I said, if you take all your angles from the positive horizontal axis going in the anti-clockwise direction like this, you add, meaning to say A is going to be added to B. There's no subtraction, there's no what, you add. And I said that one is going to be an easier part because you follow one thing. You just have to know what is the difference. So that was for a relative velocity. All right, so due to the request that we had, guys, that we have to work also on the resulting or the resultant velocity. That is the purpose of this class now. Okay, on the resultant velocity, you'll be given a condition. I'm going to explain how to answer questions so that we'll be able to understand them as we move on. Like I said, we're going to apply the components also because I explained with another way previously. All right, the information, how you take information, guys, is the same. That's why I'm not focusing much there to say this is we are going to have a north pole, this and that. No. All right, that one is the same. The resultant velocity or resulting velocity. This is where we are now. Like I said, the information, how you take the information, guys, is the same. If you check here, we are given that a bird on question number 1 is flying due east. All right. Meaning to say we have what there? We have got a north pole to be considered. Everything that we are going to have taken from the north pole, this part is not going to change, whether it's for the resultant velocity, relative velocity is the same. So given that the bird is flying due east, all right, this is our North Pole, this is the south, this is the east, and this is the west. So it is going to the east, due east. Due east means straight in the east. Due south, straight in the south. So it can be due north, straight to the north, straight to the west, that is due west. But in this case, they are saying due east. So it is straight in the east line. Guys, it is not going to be, and it will be in the east line as it is like that. So this is where the bird is flying. At what? At 7 meters per second. So we've got our bird in this case. This is the bird. Okay, let's see. Determine the resulting velocity now, which is the one that we want to talk about there. Take note, if what? A headwind is blowing at 4 meters per second from east. All right. This is the most important part that I want you to understand here. This part. They are saying there is a headwind blowing. How is it blowing? 4 meters per second from east, 30 degrees to the north. Okay, guys, the compass part, this one, you're supposed to know it, right, from your geography. Maybe you did not pass that. Let us just explain. This is your north. This is your south, your west, and your east. So it is determined with the pole first that is starting here. It's from the east. Where are we going? We are going to the north. So this is east going to the north. So we are moving to the east, going to the north. The direction is stated by these poles, the first one to the second one. So we are moving from the east, going to the north. That is the idea there. From the east to the north at an angle of 30 degrees. So 30 degrees is an assumption that we know that from 0 to 90, 30 maybe can be somewhere there just before 90 degrees. If it was north 30 degrees to the east, it means we are moving from the north going to the east direction. We are moving to the east. South 30 degrees to the west, we are moving from the south going to the west. What is written there is important. We are moving from south going to the west. It can be west 30 degrees to the south, meaning to say we are moving from the west going to the south at a certain angle that you are given. So here the wind is blowing at an angle of east 30 degrees to the what? To the north. That is what you're given. So this is our east, this is the north. So in between there, we are just saying this is this is the headwind, which is the wind in this case. I'm just gonna indicate with a broken line. This is for the wind. All right, somewhere there it is pointing, or it is blowing. So all right, so it is pointing in to affect this bed, its movement at an angle of 30 degrees. So in an actual sense, this was supposed to be like this. It was supposed to be like this, I mean, here at 30 degrees there. Okay. But I'm not going to complete that case so that we do not have a confusion also on what is to happen. So it was supposed to be like this. This is where we have our 30 degrees from east to the what? To the north. This is where it is entering. So as we know from our forces, we talked about this from the forces in N3. We said if a force or whatever that is pointing to, the way that you're going to calculate it, it's up to you. It's either you're going to take introductions of negative or you extend it to the other path like that so that you properly take your components. So if we are to extend it like this, it means if this angle is 30, remember from our vertically opposite angles, if this angle is 30, this angle is going to be also 30 degrees. So this is what we have. This is the wind, guys. This is our headwind, this one. But we take it to the other, suppose it is blowing, it is entering to the point here. It must be taken out of the point. Okay? Remember your forces. It's not like if you work it like that, it's gonna be wrong. No, it will be, as long as you understand. But the easier way that we do not have confusion from what we had before, I said it is best that you take your forces out. So you're going to take this as your force out, okay? This is your speed. I'm just referring to forces so that we understand. But here we are talking about what? We are talking about the speed. So like I said, if this angle is 30 degrees, what does it mean? It means also this one is going to be 30 degrees from what? The concept of vertically opposite angle. So this is just like a sketch. So this is our headwind, which is at what? Which is at 4 meters per second. All right, so that's it. So we've got the bed and the wind now taken on the other side, so that everything is pointing out, is taken from the point going out, not to take it inside. But if you understand even like that, you can take it, you just have to introduce a negative on a condition like that. But it can be confusing. Now in exam, you want to do this, you want to do. So just follow one thing that you are used to. So just like that, okay? Once you've got this, guys, what do you want? You want the resultant velocity. It's like we are back to. That's why I'm talking about forces. I want you to have that idea of forces. If you are given a certain force going this side and a certain force going that side, what were you doing in N3? We were finding the resultant, isn't it? That resultant is the one that we are just saying for velocity now. They were talking as a force to say, guys, I want you to get back to our N3. We talked about this. This is 5 Newton, all right? This is 4 Newton at an angle of 30 degrees. How were you finding the resultant? What were you doing, guys, that time? We were working with components. We talked about this, all right? We were using components. That's why I said I want us to get back to the components, because we are used to that. All right. I'm not saying the other method does not, because I explained other methods before. So I'm just going to focus on components, like I said. So using the horizontal component, going to have the sum of the horizontal component. Remember from our N3, the forces of the horizontal component, they take cos of theta. It's cos. So this is already in the horizontal, so you can just take it as it is. But if you want, this is an angle of 0 degrees there. So it's going to be 7 cos of 0 degrees. We add to this one, but it's where is it? It's on the negative side. Remember, the horizontal on this side is taken as a negative. So it will be negative 4 cos of what? The angle that is given there. This time we take our, because we are using this angle, we did not take the angle from the positive horizontal like I was explaining. So you see the difference between the resultant and the relative velocity. Relative velocity, we're given your velocity as they were this one and this one. But you have to turn another velocity. The moment you turn this, you find it on. It was not to say it was not pointing inside. No, it was it was on the other side. It was a correct a flow of forces that we know, or how the forces are taken. But we have to reverse. This one, we are not reversing anything. We are just extending the force to the other side as it was, in its direction as it is, and you use your components. This time you subtract, but there you just have to change the direction like this. All right? It was facing this side. Now it will be going the other side. Then take your angles from the positive horizontal up to that force, or up to that velocity. Now we are talking about velocity, not a force. But the idea still the same. So that's the difference that we have between a resultant and a relative. All right. The resultant is just a continuous. The wind is blowing. You extend it using also your knowledge of these angles, guys, from your N3 trigonometry. All right. Those trigonometry part. All right. Vertical opposite angles, this and that. That's it. You're done. At this stage, you can simplify. So this is going to give us, if you simplify properly, that's 3, 5, 3, 5, 8, 9, something like that, which is 3,5, 3, 6, right? So you're going to have this meters per second. Remember, this is velocity. Don't confuse, guys. I'm referring to forces so that you understand, but we are talking about what? Velocity there. All right. And on your horizontal components, remember, if you talk about going, being a positive horizontal, it means we are on the east side. The west is the one that is on the negative, all right? So the west is negative, the east is positive, all right? So meaning to say this is going to where? To the east. Okay, then we do the same thing for the vertical components. I hope this one, guys, we are used to this. It's just a repetition. So the vertical components will be what? All right, this is at an angle of 0 degrees, of which this one is not a vertical. So if you don't want it, you can just leave it like that. But if you want to write, you can write as 7 sine 0. Still one and the same thing. 7 sine 0. And in this case, this is the vertical that we have. And the vertical, remember, when you compare it this way, vertical, according to the horizontal that we have, on top of it, it's positive. Down, it's negative. So this means this is going to be affected. This is going to be affected as a negative because it's down, it's below the horizontal axis. All right, it's below these axes. So it's a negative that side. So that will be minus 4, the sine of what? The sine of 30 degrees. All right, that's it. Just taking everything as it is, okay? So you simplify this, we are going to obtain -2. That one was going to give us -2 meters per second. That's a vertical. Vertical, we are talking about this. Being negative, it means we are on the south. Positive to the north. So north, positive. South is negative. So meaning to say the negative that we see here is to the south. That is the one that is carries a always where you see a negative. It's in the south. When you are comparing the vertical component, the positive is where? To the north. Okay? Just like your Cartesian plan, but this is from our compass. So that's it, guys. Like I said, nothing is changing. After finding your horizontal components and the vertical components, what were you doing under forces? You were going to take this to the diagram that gives you the resultant force. This is the resultant velocity. So it's the same thing. We take our components to the diagram now, where we can see properly our horizontal and vertical. Where is horizontal? Positive. Or where are we having the east and the south? So we need a pole. This is south, this is north, south, west, and east. So we need a pole or a combination, a quadrant, which is going to carry the east and the south at the same time. There's only one quadrant that can be able to do that. That has got the east and the south at the same time. Which quadrant is this? This is the quadrant. So that is where we are supposed to have our resulting velocity. And we know that the triangle is taken like this, joined to the positive. You don't join the triangle this side. No, the triangle is joined always to the positive, which is, to the horizontal axis. So you join it back to the horizontal axis like this. So this is where we have it. To the east, this is the east one. The horizontal is the one that is represented to the east, which is what? 3,536 6 meters per second. To the south, this is -2. This is the one going to the south down here. That's where we have a -2. So this will be your resultant velocity. That's it. And the angle to be taken now can be this. You can take from the south going where? To the east, like I said. Or you can consider your angle from where? From the east going where? To the south. It's up to you. South to the east or east to the south. So this can be theta, and we can just put alpha for this one that is here. You can just write it as what? As alpha. So there are two angles there. It's up to you which one do you want to consider. All right. If you consider this angle here, the theta, it means we are moving from the east going to the where? To the south. So it's east theta degrees to the south, which is the angle that you're given that you calculate. And to calculate theta, guys, this is your mathematics, isn't it? Using of the arctan. All right, so that's it. Let's calculate the resultant. As you can see, it's a right angle triangle. So to have the resultant, you're going to use our Pythagoras theorem. That is, we are still back to the application of those forces. Remember, we are saying horizontal component squared plus vertical component squared. That is the same thing. So it is going to be horizontal, which is 3,536 squared plus the vertical, which is -2. That's -2 squared. So you're going to have the resultant velocity there. And what is the answer? If you simplify this, we are going to obtain something like 4,062 meters per second. All right. Then we have to find theta in this case. So these are the steps that you need from the diagram here. You find your components. After that, find your resultant velocity and the direction, because we need also the direction, all right? Just like a force, you're talking about a vector quantity. Direction is needed also, which is our theta or alpha, depending with which one are you going to use. So using theta, that will be opposite and adjacent in this case. So we're going to use tan. The theta is equal to arctan of the opposite, which is the vertical component over the horizontal component. So thus theta is equal to arctan. Don't consider the sign that you're given there. Even here, there's no need, guys. All right. The sign here, the negative is just to show us, remember from our trigonometry, I explained from our trigonometry and for the cast concept. All right. So the negative is just showing that in this quadrant, it's for cos. So definitely tan is going to be a negative. So that one, we do not worry about that. Just take the number as it is, 2 over 3,536. All right. So theta is going to give us, that will be something like 29. That's 29,4929, something like that. All right. So theta will be 29,493 to 3 decimal places. All right. But this is theta here. We're talking about this theta. So meaning to say our resultant, in terms of this, we're going to write this to say, therefore, our resulting velocity in this case, which is the resultant velocity. All right, resulting velocity is going to be given as what? We got 4,062 meters per second at what? This is what is affecting now the direction from the east going to the south. What was the movement from the east to the south is the angle of theta. So it's supposed to be east theta degrees to the what? To the south. But the theta, we calculated our angle theta, which is what? 29,43. So it's going to be east 29.493 degrees to the south. Or we could have worked this from the alpha. The relationship that we have between the theta and the alpha is that these two are at a point of a right angle. That's a right angle there, 90 degrees. So if these two angles give us 90 degrees, it means in order for us to have alpha, we are going to subtract the theta that we got from the 90 degrees, because these two angles are at right angle. Remember, that's 90, 90, 90 to give us 360 degrees. So it's going to be 90 degrees. Alpha is going to be 90 degrees minus theta, which is 90 degrees minus the theta that we got, the 29,493 degrees. And that was going to give us something like 60,507 degrees as your alpha. So if you wanted to write this in terms of alpha, it was going to be what? In terms of alpha, this is where alpha is. We are moving from where? From the south going in the east direction. Be careful about that. From the south going to the east. So it is going to be south 60,507 degrees going where? To the east. That is another way. That's it. That's how you're supposed to have this. So that's your resulting velocity. So the difference now, I hope you see, the difference between the resulting velocity and the relative velocity, how you calculate them, they are so different. They're so different. All right? The resulting velocity, something is affected by wind or whatever. It's a bird. We're talking about an aeroplane affected by the wind. But as for the relative velocity, you are just given two velocities, this one and this one. They are taken simultaneously, maybe at a certain point. There are two things that are being taken simultaneously at a certain point. It's not like something is affected by, but the moment we say the velocity, the velocity of this relative to that of a certain velocity, the moment it is relative to another, the one that is 2 is affected now. It changes the way it is presented, the direction. then you add your given velocities. I hope you watched the video. If not, make sure that you just watch the video so that you understand. That's the difference that we have between these two. All right. So I just hope you find this clear and just be able to revise also as much questions as you can. All right. So these are the typical questions, like I said. Let's see the other part. What are they saying here? We just want to answer one or two questions so that we'll be able to see questions that that follows, maybe question papers and so forth. On question number 2, it's just a straightforward type of a question. I want us to be able to understand this. It's a condition of a boat. They're saying that a boat can travel at 12 meters per second in calm water. So these are like still condition. When something is still, it's not affected by anything at that moment. It's a still condition. So normally, this is when something is calm or is moving on a still condition, you just present it this way, right? It is not going to be straightforward to the east. It is just going to be in between, just dividing your Cartesian plane like this. That is calm like this. All right. I hope we are together there. So the question is here, the boat that we have here travels at 12 meters per second. In calm water, it must cross a river flowing at 5 meters per second at right angle. So it must cross a river. Take note, the river flowing at. Okay, this is it. This is it, guys. Let's do this. That's question 2. We've got our Cartesian plane. Like I said, that's the most important part we have in the first place. That's our Cartesian plane here. All right, so we've got something of this nature. So the boat is moving calmly. That is in still condition. Like I said, still conditions are just presented like this. All right, those are still conditions like this. So you can just take it from this point like this way. All right. That's it, like something of this nature, okay? This is what we have for the boat, which is moving at what? 12 meters per second. So that's 12 meters per second there. Still or for calm conditions, that's how you present it, okay? So this is your north, your east here, south and west, no problem. Then they are saying here, it must cross, as it is moving, it must cross a river flowing at 5 meters at right angles. So take note, the river is flowing at 5 meters, but at what? At right angles, 5 meters per second at right angles. So meaning to say the river is taken at right angles. The flow of it or the speed of it is at right angles. At right angles, meaning to say there's no way it's going to be vertical to this line because we are talking about this quadrant. So it is going to be vertical at right angles, meaning to say it must meet at what? At 90 degrees. It is flowing at 90 degrees. So it's like it's going straight up. All right. That is it. They must meet. So it's not like here. They must meet somewhere. That is where we are talking about this. Take note. It must cross to cross there. That is meet that part, which is flowing at what? At 90 degrees. So this is crossing, going its own. The river is flowing on its own, going there upward at 5 meters per second at right angle. Calculate the velocity of the boat with respect to the riverbank as well as what? As the direction in which the boat must be steered. How the boat is supposed to be what? To be steered. So that's now we are talking about what? The resulting velocity that we are given. So in actual sense, we are this opposite velocity here that we have is the one that is on this side. All right. So it was supposed to be down, going down here, but what we have on this side is the same as what we have on this side on top. All right. It is the same, like we've got something like in this nature like this. Your velocity going down here. All right. So at the end, you are formulating what? A right angle triangle in this case. All right. The velocity that was supposed to be at right angles which is the one that we presented this way. Okay, I'm presenting to you what is important for you to understand, all right? This is how you present your diagram so that you don't have any confusion. And the resulting velocity now, that is the one that is here, because this one is for a right angle. Remember, for a right angle triangle, if you are given two velocities, this is going to be your resulting velocity. The remaining side of the triangle is going to be your resulting velocity. And the angle from this pole, we've got an angle of theta there, or you can use this one on this other side as alpha. I explained about this angle concept. All right. So meaning to say, in this case, the resulting velocity was just direct because this is a right angle triangle. There are no components to be considered there. We just have to calculate our resulting velocity straightforward. So this one is a straightforward question. Okay, apply your Pythagoras theorem. That is going to be what? Remember, the hypotenuse squared is equal to a squared plus b squared. So a squared plus b squared is equal to the hypotenuse squared. So we are talking about the shorter sides, where we have got the resulting velocity squared plus 5 squared is equal to c squared, which is 12 squared. So that is going to be rv squared plus 5 squared, which is 25, is equal to 144. Transpose this, rv squared is going to be 144 minus 25, or you can just put the square root on it on this part, which is simply the square root of 144 minus 25, because you're supposed to have rv squared, then you introduce the square root there. So that is going to give us something like 10,087. So it's going to be 0.9 meters per second. So like I said, this one is a straightforward question. There is no need for you to calculate the components there. Then the theta, which is your direction, it is going to be arctan of the opposite, which is our vertical component, over the adjacent. So the adjacent is this one, which is the what? The resulting. We are not going to take this side. Opposite over adjacent. So the opposite is 5. And the adjacent is this part of the resulting, the one that we calculated of 10,909. So take note of what you are using there. It's not going back to say arctan vertical over, vertical over horizontal, which is exactly the same. But your horizontal now is the one that is in the horizontal component here, this one, the resulting. All right. So that is 10,909. So that's it. Gonna have our theta in that case. So theta is equal to arctan. If you find this, that is going to be 24,6237 and so on, which is 24. All right, degrees. So therefore, it simply means our resulting velocity RV is equal to 10,909 meters per second. All right, so that's 10,909 meters per second at the direction now. If we are to consider this, we are moving from the east going where? To the north pole. So it's east, an angle of what? Theta, where theta is 24, the one that we got. That's 24,624 degrees, going where? To the north side. So this is going to the north. All right. So you have to be very, very careful on that condition. Okay. So that's how your questions might be given as sometimes. All right. Let's check the other part where we can apply our components, because this one, it was just a direct question, no need for components there. All right, let's check this one. A ship sails at 20 meters per second in the direction of this and experiences a current, okay, of 10 meters per second flowing from, okay, calculate the magnitude and of the resulting. Okay, this one, it's very, very important. We can go back to the application of those components. All right, so we've got a ship that sails at what? 20 meters per second east, 30 degrees to the north. All right, so like I said, the issue of the North Pole, east, 30 degrees to the north. So let's start with our North Pole first. This is question 3. So you're gonna have something of this nature. All right. That's our north in this case, all right? So we're given that this is flowing north, all right? So let me finish. Let me finish first. All right. So that is at an angle of here. It is east 30 degrees to the north. East 30 degrees to the north. I explained this as it is. It's right there, all right, here. Because I remember explaining this as it is. All right. So this one is just a straightforward, guys. We explained this at what? 20 meters per second. All right. So this is east going to the north like this. All right. East going to the north at 30 degrees. All right. That is it at 20 meters per second. All right. This is the ship. But as it is moving, it experiences a current. All right? Just like the bird that we had, it experienced what? A headwind. It is affected by a certain current of 10 meters per second flowing from the west, 20 degrees to the north. All right, meaning to say, this is what we have. This is west here. Current is moving from the west to the north, like the direction, west north. So the angle there is supposed to be like this. It was supposed to be like this. Remember the concept. This is it. The west, 20 degrees to the what? To the north. It is supposed to be here. But it is pointing inside. It's a current, it's affecting, it's like a wind. Okay. So what do? You have to extend it now because our forces, just like the forces, should be taken out of this. So you just have to extend this. So it is 20 here, vertical opposite angles, that will be a 20 there. So meaning to say, this can be just of a sketch to show, okay, it was supposed to be like this here at 20 degrees, then later on it extended. So the one that is extended, this one is the one that we are worried with, this one. This angle is 20, so this angle is going to be 20. We need the angle that is going to be taken to the horizontal. So this angle here is 20 degrees. What was the speed of this current? It was at 10 meters per second. So it is the same 10 meters per second on this side. It is just a continuation because it was facing inside. So it's just continuous with the same speed. There's no turning of this. There's nothing turned there. This is not the condition of a relative velocity where another part has to turn. Nothing turned on this one. Nothing turned or changed. All right. It's just a continuation from where it was, just continuing in that direction. So with this information, it's enough for us to calculate the resulting velocity because we just need the components as they are. Back to your N3 forces. All right. Horizontal components. So that's 20 is on the positive. The horizontal is on the positive. So 20 cos. So this is the sum. Okay, let's just put the sum there, the sum of the horizontal components. So the cosine of what? 30 degrees. Okay, we move on to another one. This one, 10, is still on this side. So the horizontal of this side is positive. So it's gonna remain as a positive. So that's positive 10 cos of what? Cos of 20 degrees. I have to consider that it's positive or negative because of the angle. All right. That time where we said we add, it is where we take our angles straight from the what? Straight from the positive to this side. You don't need to consider the sign. You just have to add everything. All right. But this one, you have to consider to say, is it this side or that side? It's because of the way the angle, guys. Can we just have a recall of our forces? I think it can help to understand more on this part. All right. So this is going to give us a positive 26,71743, which is 717 meters per second as we are calculating what? The velocity. All right. The same thing happens on the vertical components in this case. So the sum of the vertical components is going to be what? All right. So this is according to the vertical. All right. On top, it's a positive. Down, it's a negative. So this is going to be 20 sine of what? Sine of 30 degrees. Down here, it's a negative. So it will be minus 10, the sine of what? The sine of 20 degrees. This is down we are considering down there. So it's going to be a negative for the vertical. All right. And also here, remember, if horizontal to be positive, it means you are going where? You are going to the east. So you can also write that. All right. Combine this. You are going to obtain something like 6,579 like that, which is going to be 580 to 3 decimal places meters per second. And that's a positive, meaning to say we are going to the north. For a vertical to be positive, you are going up. So that's to the north. So after this, we need a diagram, not from this one, no, from this information, the diagram where we have the east and the north at the same time. Which quadrant consists of the east and the north at the same time? There's only one quadrant which has got the east and the north at the same time. That is the quadrant that we are supposed to think of. Which quadrant? That has got the east and the north. That is the first quadrant. So our triangle is going to lie in the first quadrant. And we know that from our trigonometry, the triangle in the first quadrant is presented this way. Remember, guys, all right? So you take it that from your trigonometry as it is, all right? So it's going to be like this. But this is our east, this is our north. So the horizontal, this one, the east is 26. So that's 26,717 meters per second. And this is our vertical, which is to the north, 6,580, which is just 6,5. Then we're going to calculate the resulting velocity, the angle theta, or you can use the angle alpha, this one. It's up to you for the angle. Which one are you going to take? But if you take theta, it means you are moving from east to the north. East, theta degrees to the what? To the north. If you use alpha, it's north going to the east. Okay, that will be the condition. So let's calculate our resulting velocity at the end. So RV is going to be equal to what? From our Pythagoras theorem, we are going to have the square root of the horizontal component squared, vertical component squared. So that is going to be 26,717 squared plus the vertical 6,58 squared. So this is going to give us something like 27, that's 27,515 meters per second. And what about theta? Theta from the opposite, this is our opposite, which is the vertical, and the adjacent, which is the horizontal. So it's going to be arctan opposite, which is the vertical, 6,58, over the horizontal component, which is 26,717. All right, these ones are just positive, so just take them as they are. This is going to give us 13,836 degrees. So if it is the case, therefore, we are saying our resulting velocity in this case is going to be given as 27,515 meters per second at what? Like I said, if you use this theta, it is going to be from the east to the north. So this is east, 13,836 degrees to the north. Or you can calculate this angle alpha. You subtract 90 minus this, you get your alpha, but it's going to be 90 degrees alpha to the east. We are moving, N, which is the north, alpha degrees to the east. We are moving from the north to the what? To the east, if you're considering alpha. I hope we are together there. If you're considering alpha. All right, so I want us to work as much questions as we can. These are the typical questions that you might be given in this case. So we've got a question paper here. We're gonna try to work this one, question paper revision because of our time, but you can try as much questions as you can. There we are given. We want to see how do they ask these questions. All right. An aeroplane, or so an aircraft with an airspeed of 330 kilometers per hour takes off from OR Tambo International Airport in the direction of north 35 degrees to the west. Okay. We are moving from where? From the north to the west. Okay, let's do this. This is what we have here. Gonna just say for North Pole, something of this nature. That's our north, south, west, and east. So they're saying the aircraft with an airspeed of this, the direction, there is the motor, north to the west. We are moving from the north going to the west. That's the direction. From north to the west, the direction is supposed to be facing west at an angle of what? 35. So it's somewhere here. All right. This is our aircraft. North to the what? To the west at an angle of 35 degrees. All right. And this is the speed, which is the velocity, 330 kilometers per hour. Okay, that's our velocity, which is our airspeed, I mean. All right. The aircraft is blown off. There it takes off. It is on its own. Now it is blown off by a wind. Not to say it was its no. It is moving at its own speed. Now it's blown off by a wind at 90 kilometers per hour. Where is the wind coming from? From the west. 42 degrees where? To the south. Meaning to say we have got a condition of this wind. It's blowing. This is our west, south. In between is blowing this direction. This is the wind there. So that it affects this aircraft. Okay? At an angle of 42, west 42. This is west going to the south. So the angle is here, 42 degrees. But like I said, you're going to take it outside because this is facing into, so you take it to the other end like this. So meaning that it was going to extend. The wind was blowing like this. This was our wind blowing. Sorry for that. All right. This is our wind blowing. But as it is blowing, we're just going to take it to the other side because it is going to face inside like this. So we take it off the other way. This is where we're going to have it. So if this angle is 42, this angle is going to be 42, vertically opposite angles. So the angle here is going to be taken as an angle of 42 degrees. And what is the speed of the wind? It is blown at 90 kilometers per hour. That's it. That's it. That's the idea there. At 90 kilometers per hour. So as we know, we're gonna need to calculate the resultant velocity of the aircraft. How are we going to calculate the resultant velocity? Like we said, using the components. I'm not saying this is the only method. No. We explained other methods, but using the components, we are going to take this angle to the ground, this one. It was given north 35 degrees here, but what is the angle between the pole and the what? The aircraft here, between these two. This is the angle that we consider, just like 42. We want to consider this angle here. So that's 90 minus what? Minus 35, because this is at right angles. So this is going to give us 55 degrees. So we are going to use the angle of 55 degrees instead. So meaning to say our horizontal components, if you are someone like me, going to take it like this, 90 cos 42. We are on the positive, so it's going to be a positive 90 cos 42 degrees. This side is on the negative, so it's going to be negative 330 cos of what? The angle between here from the horizontal, which is what? 55 degrees. All right, so that is going to give us the sum of the horizontal components, which is, in this case, it was going to give us a negative. That's negative 122,397. Meaning to say that, what does it mean? It is simply means if horizontal is negative, it is going to the what? It is going to the to the west. This is the west side where it is what? Where it is a negative. It simply shows that it is going to the west. All right. The same thing on the vertical components. In this case, you're going to have your vertical components in this case, whereby we are considering on top, above here as a positive. Everything on top is above, it's a positive. So this vertical component here, it's on top, it's going to be a positive. It's above x. So this will be 90 sine of what? Of 42 degrees as it is, plus also this side is on it's above, so it's a positive. So it's going to be plus 330 sine of what? Sine of 55 degrees. So this is going to give us the horizontal component. I mean, the vertical component, which is going to be a positive. That will be 330,542, right? 542. That's it. Kilometers per hour as a speed. All right, so we have got our vertical component. There we have our horizontal component. With these two, we are supposed to take them to the diagram. We know that this positive simply means we are going where? To the north. So we are going to need a quadrant which is going to carry the north and to carry the west. The direction, it is because of the direction. That's why we have to consider that. If it was not because of the direction, we don't even consider, because the resulting velocity, just use apply Pythagoras, we are done. But the direction now, you're bound to know where the quadrant is, so that the angle to be taken, you understand the angle, how you take it. It's because of that. So which quadrant are you going to take where there is the west and the north? The west and the north is in the second quadrant. All right. From our trigonometry, guys, we explained these things. In the second quadrant, I said your triangle is going to be like this. We check even complex numbers. I explained how you draw your triangle under complex numbers, how you draw your triangle under trigonometry in the second quadrant is the same as this part. So you don't change because you are dealing with engineering science. No, these are mathematics. The engineering science, it's played its role here. That's where it ended. Now this is not science. This is maths. The science just gave you this concept to say if the wind is blowing, then you take it that side. That is where we are talking about the science concept, the diagram, this and that. Even the idea of this, these are mathematical calculations always, because you're now considering how to even consider your angles. It's maths. So do not panic about this. In the second quadrant, that's how your triangle is going to be like, remember? So this being our resulting velocity going up here, and just consider our horizontal and so forth. Horizontal, which is negative. This is the horizontal side, negative 122,397. The vertical, which is this side up here, which is the north, which is 330,542. So that's it. We can calculate our resulting, then the angle theta as the direction, or you can use alpha here as your direction. It's one and the same thing. So the resulting velocity from our Pythagoras theorem now, what is going to be our resulting velocity? So the resulting velocity from the Pythagoras theorem is going to be the square root of horizontal component squared minus 122,397 squared plus the vertical component squared, which is 330,542 squared, like this. So that is going to give us the resulting velocity, which is going to be 352. That's 352,4755 and so on. So that's 558, which is going to be 476 in kilometers per hour. Okay. Then for theta, as the direction now, that's arctan of the opposite over the adjacent, which is the opposite is what? Is the vertical component of 330,542 over the horizontal component. But like I said, do not consider the sign. The sign, they don't, as you want the angle, there's the sign there is for your trigonometry part, guys. Don't consider that. I also explained this even when you are calculating, remember, when you are calculating the reference angle, you don't use the angle, you don't use the negative sign, okay? So arctan of this is going to give you something like 69,6808, which is 681 to 3 decimal places. So I've got our resulting velocity and also its direction. So therefore, we're going to have our RV. That's our RV is going to be 352,476 kilometers per hour. All right. At the theta now, the theta that you're given, we have to analyze where our theta is because, like I said, we can use theta or we can use the alpha. Using theta, it means we are moving from the east going to the north. These are the poles that you are working with, 2 poles only, east and north. So you are moving from the east going to the north, direct to the north pole. So it's east theta degrees to the north. So it's going to be east, the angle that is here, east theta, which is 69,681 degrees, going where? To the north. All right. Or we could have referred this in terms of alpha. This is our alpha here. Representing in terms of alpha, it is going to be 90 degrees minus theta to obtain alpha. All right? Which is 90 degrees minus the angle that we got here of 69,681. You're going to obtain something like 20,3, that will be 20,319 degrees. But in terms of alpha now, the direction is going to change because you are moving from the north in this direction, going where? Where are we going there? Guys, what? Okay, sorry, guys. You see what is happening here, guys? We said we have got the west there. Why am I writing the east? Why am I making mistake? At the last minute, you see these things, what they do, guys. This is our west here. That's our east. And I wonder what is happening here. Guys, very sorry. This is east and this is west here. All right, no problem. Very sorry for that. That is west, guys, this side. It's because maybe I'm tired, 1 hour. Okay, maybe it's because of being tired, guys. You know, these recordings, no problem. So like I said, this side is gonna be north to the west at an angle of what? Alpha degrees. So this is north going to the south, to the west. Are we together? North going to the west at an angle of 20,319 degrees. So that means in this case, you can write it in this way: north at an angle of 20,319 degrees, going where? To the west. All right. So it's either you're moving from the west to the north, because you have to consider the poles that you had here. You had west and north. So your answer is supposed to be bound by those poles, west, and it's supposed to be in between those poles. There's no way we're gonna have west and south, north here. Then we see now here our answer is now northeast. There's no miracle like that. That miracle does not exist in our mathematical calculations. I'm saying you found your components this way with west and north. Then your answer does not carry what you had on the components. For the resultant velocity, check your N3. We did this in N3. We talked about this. Check it properly. There is no miracle like that totally. So guys, make sure that you revise your work before answering. The poles here are the same that you're supposed to have on your final answer, but depending with where are you coming from the west to the north or from the north to the west. All right? Is it from the north to the west, or is it from the west to the north? You are starting from the west going to the north. That's why I put the arrow. These arrows that they are not for design. They are meant for direction to show us that we are moving from north to west. We are moving from west to another pole. All right, just like that. So guys, more revision to come, more question papers to come, introductions to come on each and every part. As we request these introductions, I do bring them. So that's it. It might take time, but I do respond. But for now, guys, that's it till we meet again.